Hi, welcome to Chapter 4. Chapter 4 begins the second unit of this course. This Unit 2 focuses on chemistry. First, we will cover the very basics of chemistry. That's this chapter, Chapter 4. This is going to be a review for everyone who's taken chemistry already, and it should be a fairly simple review, so we're only going to spend 1 week on it. If you haven't taken chemistry yet, this is hopefully a gentle introduction to chemistry, and it will help you when you do take chemistry. I don't want you to stress over this chapter, um, even though we are going through it fairly quick. There are a couple things in this chapter that the book covers that I'm going to tell you you don't need to worry about. And one of those things, if you do understand it, then it's extra credit. Uh, After chapter 4, chapter 5 is going to be on energy. We'll spend 2 weeks on that one. And even though a lot of that's going to be review for those who've had chemistry already also. And then we'll have our next exam. So our next exam was going to be chapters 4 and 5. We're going to have 3 weeks of instruction before our next exam. Okay. Then we'll have chapter 6, which is on ions. We're going to only spend 1 week on that one. Again, because it's quite a bit of review for the students who have had chemistry. And finally, we'll cover water and its role in chemical reactions and its use in food. And that one we'll do 2 weeks on. So we'll have 2 exams in a row that will be 3 weeks of instruction before the exam. Okay. For students who've not had chemistry, again, I don't want you to stress too much about these chapters, especially the ones that we're only spending a week on. The ones that are just a week, even though it's going to be kind of jam-packed, just keep in mind that it's only going to be 1/3 of the exam. So the exam is going to be structured points-wise based on how we've covered it over the 3 weeks. So if we've only covered it 1 week, it's only 1/3 of the exam. And there are certain parts of the chapters that I will tell you, don't worry about this. I think a lot of it is presented at a very basic level, such that it might even be review from some of your middle school science courses. Hopefully it is, and there's really absolutely no need to stress. But if you do have any trouble with anything, I am always available to do some extra explanations for you. Just give me a shout, and I will be happy to explain anything, spend some extra time with you if you're not understanding anything. Okay. So just definition of chemistry is the study of the makeup, structure, and properties of substances and the changes that occur to them. And with chemistry, it's the study of matter, and that is anything that occupies space and has mass. And so that doesn't matter whether it's a liquid, solid, or gas. All of those occupy space and have mass. The atom is the smallest unit of any elemental substance that maintains the characteristics of that substance. So that's the definition from the book. I'm going to give you a few more definitions so you really understand what an atom is, because that's a long, kind of wordy definition. Okay, the basic unit of a chemical element. So you have a chemical element, whether it's oxygen, carbon, titanium, iron, and the smallest basic unit that you can have of that element is an atom. It is the basic building block of chemistry. It's the smallest particle of an element that can exist either alone or in combination. The smallest part of a substance that cannot be broken down chemically. So elements. An element is a substance that contains only one kind of atom. So we have the periodic table of elements, and so if you have lots of atoms of oxygen, you just have that element in front of you, oxygen. Okay, so there are 88 to 94 naturally occurring elements on Earth. that naturally occurring depends on whether you include elements that are only found in extremely trace quantities. Like it's almost impossible to find them. All artificial elements that exist, so there's an additional 24 that have been produced artificially. All the artificial elements that exist are radioactive with very short half-lives. They degrade very quickly. The book actually says 27 instead of 24, and I don't know if maybe they're saying 27 because some of those naturally occurring elements have also been created artificially, or if something's out of date. I'm not really sure. But there is a discrepancy there. I'm not testing you on that. But so the atomic symbols, sorry. So what an element is determined by the number of protons in the atom. And notice I'm not saying electrons or neutrons. It is just the protons determine what that atom is. And symbols, which are just abbreviations using letters, are used to identify them. The atomic symbols are often easy to figure out, such as carbon is C, oxygen is O, but not always, because sometimes they are based on Latin names. So for example, iron is Fe, and that is because the Latin name for iron is ferrum. Sodium is Na, and the Latin name is natrium, and etc., etc. Copper is cuprum. So if it has a chemical symbol that seems to make no sense based on the actual name of the element, it's probably because the Latin name is what's used for the chemical symbol. So looking more in depth at an atom, at the composition of an atom, the atom has a nucleus, which is the central core of the atom, and that nucleus contains the protons and neutrons, and they're kind of all mixed together, jumbled up. Each proton and neutron has a mass of 1 atomic mass unit, which is a special way of measuring mass of the subatomic particles. And then on the not exterior, but outside of the nucleus are the electrons, and the electrons are kind of contained orbiting the nucleus in an orbital, and each orbital has 2 electrons. And the charges of each of these particles is really important. So protons are positive in charge, neutrons have no charge, and electrons have a negative charge. I'll also point out here the electrons, the atomic mass of the electrons is very close to 0. It's not exactly 0. There is still some mass. Electrons are matter, but it's very close to 0, so much that we really don't even count the electrons as part of the atomic mass of an atom. The protons and neutrons, so as I said before, the number of protons is what determines what the element is. And generally, the protons and neutrons are equal in number, but not always, even in the same element, because we do have what are called isotopes, which are just different numbers of neutrons within different atoms of an element. And those isotopes have different radioactivity and behave just somewhat differently. So the electron, going back to the electrons, so their mass is almost 0, but they take up the majority of the space in the atom. You can see in this, switch my laser pointer, and this diagram of the atom, the nucleus is a very small amount of the overall space of this atom. Now, the difference in the charges between the protons in the nucleus and the electrons in the electron orbitals causes those electrons to always be moving. And so they are, in fact, orbiting the nucleus of the atom. They move in pairs, orbiting that nucleus. And so each pair and the space that they occupy is called an orbital. As the number of electrons increase, the shape of these orbitals can change and the distance from the nucleus expands. If you have a smaller number of electrons, then they're all going to be closer to the nucleus, but as you increase the number of electrons, this overall size of the atom expands. Okay, I forgot to point out earlier, number of electrons in general, you have the same number of electrons as you have protons, but not always. There are exceptions called ions, which we will discuss later on in this chapter. Okay. So the atomic mass, when we are looking at the periodic table, the example of an element in the periodic table. So our atomic number identifies the element, and that is based on the number of protons. So carbon is 6-proton atom. We have our symbol, right, our element name, and our atomic mass is the mass in atomic mass units of the average atom of that element on Earth. So I mentioned that there are isotopes and with different numbers of neutrons, and since protons and neutrons make together the total mass of the atom, you don't always have a very neat number, right? So if you have a carbon atom that has 6 protons and 6 neutrons, well, then the atomic mass would be 12. Right? It's 12 atomic mass units, adding up the protons and neutrons. But there are isotopes out there of carbon that have more or fewer neutrons. And so the average of all of the isotopes of carbon on Earth that we know of is actually 12.01 atomic mass units. And so that's why this atomic mass is slightly different than just simply adding up 6 plus 6 protons and neutrons. Okay, okay, I'm going to be going over a lot of this in a slightly different order from the book, an order that I think makes a little bit more sense, and if it doesn't, I'm sorry, but just heads up, it's a little bit different order from the book. So here I'm going to be talking about electron shells. So I just talked about orbitals, and so electron shells are kind of related to that. An electron shell is the area of space surrounding the nucleus that has one or more orbitals. So if we look at this, like these are the electron shells. There's actually there's one denoted here in blue, and then there's another one in purple. Okay, so orbitals, they can have different shapes and distances. Okay, we're not going to go over the shapes in this course. You'll learn about that in chemistry, but the key about the distances is as you increase the number of electrons, those orbitals are going to be further out away from the nucleus. Okay, the first shell has only one orbital in it. Every orbital remember, has one pair of electrons, so it has 2 electrons. And so the first shell, which is going to be what we're seeing here, we're talking about shells here, not orbitals, has only one orbital, and so therefore it only has 2 electrons. So this is potassium, and you can see in this first shell, and this is just a diagram, this is not at all what like what this actually looks like in the atom. But it's a simplistic diagram to just show the shells. There are only 2 electrons. Okay, every shell thereafter is going to have up to 8 electrons. And so they'll have 4 orbitals that those electrons are spread out between. And so here on potassium, you have the second shell and it has 8. Then the third shell also has 8. And so here we're at 2 plus 8 is 10, plus 8 is 18. And then there is 1 here on the last shell, this fourth shell, and that should make total sense because we've got an 18 and then just 19 total electrons in this diagram. And if you look at the atomic number for potassium in your book, it is 19. Okay, so the 19 electrons. Okay. Okay, so the electrons in the outermost shell is a key word here. It's called valence electrons. And these are the electrons that we are most concerned about and have the most importance when it comes to chemical bonds. The key thing to understand about this valence electron shell is that atoms are most stable when the outer shell of electrons is full. Okay, the atom wants its outer shell to be full of 8 electrons. And so it's going to do what it can for that to happen. And that is how we get chemical bonds. So the periodic table. Periodic table is amazing. Okay, this is the one from the Berean Builders Chemistry book. I really like it. So with the periodic table, we have the atomic symbols. It tells us so much about each element. We have the atomic number, so that's the number of protons. We have the atomic mass, the protons plus the neutrons. The columns, these are called groups. Each column is called a group. And rows are called periods. So periodic, right? We have things grouped by nonmetals. We have the standard metals, we have the transition metals, the post-transition metals, the metalloids, and intertransition metals. Okay, we have, and the way these are grouped is just like, there's genius behind it, both from a creation perspective, because God did this, and like the numerical, like God is behind this, but the scientific mind that discovered this too, it's amazing. So when elements are in the same group, when they are in the same column, they will have very similar characteristics. They will behave similarly. And so hence why the table, it is so nice, neat, organized, where all of the metals are together and the transition metals are together and the non-metals are together with the exception of hydrogen. And it's all because generally when elements have the same group, they behave similarly. Now there's some differences here, right? But in general. So let's ignore the transition metals for a second. And the other thing about these groups, so we're focusing on the groups that have A on them, is the group number of these A groups corresponds with how many electrons are in the valence shell. So the 1A group has 1 electron in the valence shell. 2A has 2. 8A has 8. Okay. So in that outer shell determines a lot of the properties of the elements. So all the elements in column A, for example, column 8A, are our noble gases, right? They have 8 electrons. And they're called noble gases because nobility, it was highly esteemed, right? They're perfect, not really, but thought to be. And they're called noble gases because they are extremely stable, because like I told you, all atoms want to have 8 electrons in that outer shell to be stable. So these 8A group 8A atoms are extremely stable because their valence shell has 8 electrons. Okay? They don't interact with anything. They don't need to. They do not form bonds. Conversely, elements in column 7A have 7 electrons in their outer shell. And to be stable, they want to have 8. So they will try to interact with other elements, with other atoms in a way that they can borrow or share an electron with something else. Okay, so the 7A atoms are called halogens. And so this comes from the Greek hal, which means salt, and gen, which means produce, because they all produce salt with these 1A groups, such as sodium and potassium. So they are highly reactive. They're almost never found as single elements or unbound, and they're usually found as what we call homonuclear diatomic molecules, which means you don't just find a single fluorine floating around. You find it as a molecule of 2 fluorines bound together. And the same goes for all of these up to iodine. Now, our bodies and our nutrition needs are 99% made up of, I'll say almost completely made up, just 21 of these elements. Okay, 99% of our bodies are actually just made up of 4 of these elements, and those would be oxygen, carbon, hydrogen, and nitrogen. Okay. Then we also have elements that are essential for us in our diet, such as calcium and phosphorus. We need smaller amounts, so we need lots of calcium and phosphorus in comparison to a lot of these others. We need smaller amounts, but they are also considered very essential, of potassium, sulfur, sodium, chlorine, magnesium, and iron. And iron right here. Okay, and then we need even smaller amounts of what we consider trace amounts of several others. So fluorine and zinc and copper and iodine, manganese, molybdenum, which is MO down here, selenium, which is SE. Some of these I'm not even as quick because we don't use them a whole lot. Chromium, which is CR. Where are you, chromium? Right here. And cobalt. All right. So 21 total. Oops. Yeah, 21 total. Oh, and they were all, I forgot they were all going to be highlighted in my neck when I clicked over. Okay, so some of these are mentioned in the book, some of them are not. I think cobalt I added. Cobalt, we really just need it in the form of vitamin B12. And the book doesn't really mention the 4 biggest ones, hydrogen, carbon, nitrogen, and oxygen, as ones that we need in our diet. And it's really just because you're automatically going to get them in your diet as long as you're eating something that's organic. Because everything that we eat is made up of hydrogen, carbon, nitrogen, and oxygen. Unless you're not eating any protein, and then you might have a nitrogen problem. But, okay, so this, I've already shown you this slide. I'm just going to show you a little bit more. Okay, so for example, we have sodium, and sodium, we have the first electron shell is going to have 2 electrons, okay? And sodium on our periodic table, let's go back to that real quick. Sodium is number 11, atomic number 11, so it's going to have 11 electrons unless it's an ion, which we'll talk about later. So we're going to fill it in with 11 electrons. So first electron shell has 2, second electron shell has 8. Okay, so now we're up to 10. And so now we are going to fill in 1 more electron shell, and it's just going to have 1 lonely electron there on that electron shell. Okay, the next one that we're going to look at is chlorine. So chlorine has an atomic number of 17. So chlorine, we're going to fill in those electron shells. So we have 2 plus another 8 on the second shell, so that's 10. And so 7 more to fill in, and so it looks like that. So 7 on its third electron shell. Okay, so chlorine was in group 7A, and sodium group 1A. Okay, so now because sodium has just 1 electron in its third electron shell, it wants to have 8. And the easiest way to have 8 in its outermost shell is actually to just get rid of the 1. Because then its outermost shell is the second shell. Okay? Chlorine, on the other hand, also wants to have 8 electrons in its electron shell. And the easiest way for it to get that is to take an electron that is just out there that something else is trying to give away. So atoms can lose or gain electrons as needed. So that's why I say that in general, they have the same number of electrons as protons, but not always, and they actually can be more stable if they lose or gain electrons. Okay, so sodium wants to give away its extra electron, chlorine wants it. Both atoms are more stable that way. And when they do this, when sodium does give away its electron to chlorine, sodium is now has a charge, because now it has more protons than it does electrons. Okay, it has 11 protons, and now only 10 electrons. So it has a positive 1 charge because it lost 1 electron and has 1 more proton than electrons. The chlorine, on the other hand, now has a negative 1 charge because it gained 1 electron. So now it has 18 electrons and 17 protons. And so it has a charge of negative 1. So when the charge, and so now you have a negative charge and a positive charge, and they're going to be attracted to each other because opposite charges attract. Now, when the charge on an atom is no longer neutral, when this sodium has lost its electron or the chlorine has gained an electron, this is called an ion. There's a special name for an atom that has a charge. So, talking a little bit more about ions, we have cations, which is the name for positively charged ions. Okay, easiest way to remember that for me is that there's a plus in the name. That T in cation looks like a plus symbol, so it's positive. I have also heard another way to remember this is that cats have paws. So positive. Okay, so sodium is a cat, when it is in the ion form, is a cation. An anion is a negatively charged ion. And for me, the way to remember that is that there's an N in the middle of the name, anion, and it stands for negative. Right? So chlorine, the chlorine ion or chloride, is an anion. Okay, so ionic bonds. The sodium gave an electron to the chlorine, so now it has a positive charge. The chlorine gained an electron, and so now it has a negative charge. And we give that charge a number based on how many electrons it has less or more of. So the sodium has a positive 1 charge, the chlorine has a negative 1 charge. Okay, opposite charges are attracted to each other, and so now these two atoms will form a chemical bond called an ionic bond. Okay, and so an ionic bond, the actual definition is a chemical bond in which the electrons are transferred. So sodium has given it away from one atom to another, causing both atoms to have a charge. Okay. Ionic bonds are always going to be between metals and nonmetals. The metals will have the positive charge and the nonmetals will have the negative charge. And they tend to form crystalline structures because the atoms still have a charge, okay? Even when they're bound together, it doesn't just cancel out. So you have the sodium and chloride here, and this chloride is negative, and it's still going to be repelling any other negative because like charges repel each other, okay? Then the sodium, which has a positive charge and is bound to the chlorine, but it still has a positive charge, so it's going to be repelling anything positive. And so it's because it's pushing away like charges and still kind of attracting opposite charges, you get this nice crystalline structure in ions, or in ionically bonded molecules. Okay, so let's talk about compounds and molecules now. So we kind of already introduced a compound because we're talking about ionic bonds, and those are creating compounds. But let's get into it a little bit more. So a compound is a group of 2 or more different elements that are chemically bonded together. This is different from what is in the book. Okay, and this is actually a problem I have with the book because it makes it really sound like compounds and molecules are the same thing, and they are not. Now, I'll get into this, but compound specifically, a group of 2 or more different elements that are chemically bonded together. So you cannot have an oxygen and an oxygen form a compound, right? Because the oxygen and oxygen are the same element, okay? So it has to be 2 different elements, so like sodium and chloride. A molecule is just a more simple name of 2 or more atoms bonded together. So if you have oxygen and oxygen, it is a molecule, just not a compound, okay? If you have sodium and chloride, it's also a molecule and a compound, okay? So that is the key differentiation there, is that molecule is any group of atoms that are bonded together. Compound, they must be different elements. A chemical formula then is the combination of symbols of the elements that make up the molecule. So it's just the symbol representation of the molecule. So examples, sodium chloride, NaCl. So this is a compound and a molecule. Potassium chloride would be also a compound and a molecule. Both of these are ionic bonds. Oxygen. So oxygen is generally not going to be found as a single atom. It always forms bonds with other oxygens, and so it's found as O2. It's also found as O3 and ozone, but this is a molecule, but it is not a compound because the elements are not different. Okay. H2O, which is water, okay, is a molecule and a compound. Okay, group of two or more atoms, and there are different elements. Okay, so even though there's two hydrogen, there's also oxygen, so there are different elements that are part of the molecule. Okay, C2H4O2. This is also known as acetic acid. Okay, and we'll get into this for a second. So when we are looking at a chemical formula, we have the symbols which represent what elements are the atoms are in the molecule. But then sometimes we have numbers. Okay, so a number as a subscript means that there are that many atoms of that element as a part of the molecule. Okay, if there is no subscript, then it is an assumed 1. Okay, so for NaCl, for sodium chloride, there is 1 sodium and 1 chlorine. For potassium chloride, there's 1 potassium and 1 chlorine. For oxygen, there are 2 oxygen atoms. For H2O, there are 2 hydrogen atoms and 1 oxygen atom. Okay, for this acetic acid, there are 2 carbon atoms, 4 hydrogen atoms, and 2 oxygen atoms. Okay, now this last formula here is also acetic acid. It's just written a little bit differently because if you look at what the actual structure looks like as far as which atoms are bonded together, you have a carbon atom here that just has 3 hydrogen bound to it, not all 4 of the hydrogen in the molecule. Okay, then there's a 4th bond with another carbon, and then this carbon is bound with 2 oxygen, and then this last oxygen is bound to that 4th hydrogen. Okay, so instead of writing it all together like this, it's written separately so that you can see that CH3, there are these 3 hydrogen are bound to the first carbon. Then you have the second carbon, which is bound to oxygen, and another oxygen that has hydrogen bound to it. Okay, so this way of writing the formula is also correct, and it's called a structural formula because it just gives you a better indication of what the molecular structure is of that compound. Okay, so I've already kind of talked about this, but when we are talking about ions and the periodic table, you can basically just use the groups to know what the charge is going to be on the ion version of the element. Okay, so in group 1A, the charge is going to be positive 1, 2A, positive 2, 3A, positive 3. 4A, they actually don't form ions because they have to either give away 4 or gain 4, and it requires too much energy to do it. So they don't do it. In 5A, it's now they would gain 3 electrons, and so they are -3. 6A wants to gain 2 electrons to have 8 in their valence shell, so it's -2 charge. and 7A is -1. And the noble gases are never going to be ions. Now, the transition metals, they are just kind of their own little animal. They're variable, but just know that metals are always positive. Okay, now covalent bonds. So covalent bonds are formed when atoms share one or more pairs of electrons. So they're not giving it away. It still belongs to them, but they're going to share it with another atom so that that other atom can also have 8 in its valence shell. So example here is water. So oxygen has 8 total electrons. Okay, the first 2 are in that first valence shell, so the second valence shell only has 6. Hydrogen only has 1 electron. Okay, so we just have 1 electron in that hydrogen in its single valence shell. Now remember that the first valence shell can only hold 2 electrons. Okay, so hydrogen, its valence shell can only hold 2, and when it holds 2, it's stable. So what it's going to do is it has this 1 here, and it's going to share this 1 with oxygen and also share one of oxygen's electrons. And so therefore it has 2 and it's happy. Okay, and it's going to do that on both sides. Now, if you look at oxygen now, because the hydrogens have each shared 1 electron, oxygen now has 8 in its valence shell, and it is also stable. And so this is what a covalent bond is. Covalent bonds can also be double bonds or triple bonds where they're sharing even more than 1 pair. Okay. And so here's an example of a double bond. You have carbon, which has 6 total electrons. So you're going to have 2 in the first shell and then 4 in its valence shell. You have oxygen, which again has 6 in its valence shell. So each oxygen needs 2 to get 8. And the carbon needs it needs a total of 4 to get 8. Okay, so the oxygen will share 2 with carbon. The carbon will share 2 with each oxygen. Because you have 2 oxygens sharing 2, the carbon is getting 4, and each oxygen is getting 2, and they're all happy. So you have 1, 2, 3, 4, 5, 6, 7, 8 for oxygen, 8 for carbon, and 8 for the other oxygen. And so this is a double bond when there are 2 pairs of electrons that are being shared between the atoms. Okay, so let's get away from all of the atomic talk and just talk a little bit about how we classify matter. This is on page 101 in your book, figure 4-9. I would know this. This is a strong hint about the exam. Okay? Because you will be asked to reproduce this. Okay? Now, I have put this on its side rather than going up and down. It's the same thing either way. Okay? So we start with all of matter can be divided into pure substances or mixtures. So pure substance means that it is just one substance in there. It is just either, that's pretty simple, right? So examples I have here are water, sugar, okay? And anything else that is going down the line would actually be an example of a pure substance. Mixtures are exactly what it sounds like, mixtures of multiple different chemical substances, okay? So a salad is an obvious mixture, but milk is a mixture. Now, it's milk, right? But milk on a molecular level has lots of different things going on with it, right? There are fats, there are proteins, there is water, and there are multiple types of fat. There's multiple types of proteins in the milk. Okay. So to our eye, it looks like one pure substance, but there is a lot chemically going on within milk. Okay. Now, pure substances, we're going to just follow this all the way through now, can be divided into compounds and elements. I'm going to start with elements first. Now, in this, I tried to give food examples. There really aren't many food examples for elements that you're going to add directly to a food product. The closest thing might be iron. So like iron is added to fortify cereals, for example. But even that, it's usually added as a compound, like ferric phosphate. But iron, calcium, zinc, those are elements that are used to fortify foods. They may or may not be added as in the elemental form. Usually not, because it's not as stable that way. But now compounds is a lot easier because there are lots of compounds that we use in our food. Water is a big one. But for example, baking soda is just a single compound, chemical compound that is packaged and we add it to our food. Sugar is another one. It's just single compound that, single chemical that we add to our food. Now, compounds can be divided into organic or inorganic compounds. So organic compounds are any compounds that basically include carbon as a base. Okay, so you heard carbon-based life forms. Organic is carbon. Okay, so all of your sugars, your fats, your proteins are carbon-based. Okay, so some examples of organic compounds that we use in our food. Again, sugar, oil. Generally, it's just one type of oil that is together, so it's still considered a pure substance that we'll add. Protein is a little bit harder because, like, if you think about our protein sources like eggs, milk, meat, it's multiple different types of protein, so it wouldn't be considered a pure substance. But one example would be like whey powder. So that is just one protein, whey, made into a powder, and that would be a food ingredient. Inorganic compounds then don't have carbon as their base. And so some examples of those would be water, salt, okay, H2O, and sodium chloride. Now, going into mixtures, those can be divided into two types, homogeneous and heterogeneous. So homogeneous means that it is a mixture, but if I take a scoop of it and I take another scoop of it, those scoops are going to be identical, essentially. Okay, so the mixture is mixed so well that it doesn't matter if I take a big scoop or a little scoop, the chemical makeup is going to be the same across them. Okay, so some examples I have for you, and there's plenty more, but coffee or tea would be one. Hard candy would be a homogeneous mixture. So I tried to think of some that weren't necessarily liquids, but hard candy would be one. Okay, if you break that into tiny pieces and you analyze those pieces, you will have the same mixture of substances in one piece as another. Vinegar. Now, vinegar, you might be tempted to say, well, wait, that's a compound. But the vinegar that you buy in the store is mixed with water. Okay, so it is a mixture of acetic acid and water. It is not pure. Okay, then heterogeneous mixtures are mixtures that the substances are not dispersed perfectly evenly. They are not perfectly mixed. So the first two are kind of straightforward, right? So spaghetti, one bite of spaghetti is not going to have the same things as another bite, especially if you have small bites, right? the Italian salad dressing, you can actually see the bits and pieces floating in there. So if I take a very, very tiny sample of Italian dressing and another tiny sample, well, one might have a big piece of ingredient and that another one doesn't. Okay. Now dough you might be tempted to think is homogeneous because it looks all the same, but actually it's heterogeneous, and that's because the water that is mixed in with dough is actually it does not become, it kind of hard to explain, but it actually is surrounding the proteins and not incorporating or into them, and so you get pockets of water in it. Now, this is like on a super like microscopic level that it's not homogeneous, but it's technically a heterogeneous mixture. Okay, so when we have mixtures that are liquid mixtures, although we could talk about this with solid or gas too, but typically we're thinking liquid. We call these solutions, okay? And so some key terms here is that the solute is the material that is dissolved into the solvent. So we have salt water. Salt is the solute, and water is the solvent that causes the dissolving, okay? And then the total is the solution once they are all mixed. So the salt water is the solution. Water is the most common solvent, but it's not the only solvent, and we'll probably see that in some of our experiments in this class. Okay. Going over physical and chemical changes. So physical changes are any time that we are just changing the size, shape, the physical state, which is like solid, liquid, gas, or the temperature, without changing the chemical identity. Now, if we change one of these things and the chemical identity changes, it's not a physical change anymore. It's going to be a chemical change. So some examples are cutting meat, grinding meat, making flour. Okay, you haven't changed the chemical identity. You've just broken it up into smaller pieces. Freezing meat, melting butter, as long as you don't burn it. Okay. Now a phase change, when we go from solid to liquid, gas, and vice versa, these are reversible physical changes. Okay, so if we freeze a piece of meat, we can then thaw it and it goes back to solid, right? If we freeze water, we can thaw it and it goes back to water, and then we can make it a gas, and then we can go back to liquid, right? This is reversible. Now, if the temperature starts affecting proteins and things, sometimes that's not reversible, but that's different than a phase change, right? Because we're actually causing a chemical change in addition to the phase change. So keep that in mind. But if you were just purely having a phase change going from solid to liquid to gas, then that is reversible. And it is a physical change, not a chemical change. Chemical changes generally are not reversible. I'll say that. So a chemical change occurs whenever a new substance with a different chemical and physical property is formed. So some clues when a chemical change is happening would be when the color or odor changes, such as this rotting banana. Okay. When the flavor changes, such as when we are browning our meat. Okay. And that changes the color too, right? And the odor. Release of gas. So when you bake a cake and the cake rises, when we are making Swiss cheese and all of a sudden there are holes in the cheese. How did that happen? Maybe we'll learn that this year. Changes in texture can definitely be another one. So when you cook an egg, that texture definitely changes from liquid to a solid egg white. When you are extracting gluten, making dough, that texture certainly changes from a flour water mixture to the dough that you make. Okay. All of these are indications of chemical changes. Now, gas isn't always an indicator. So like, for example, when you open a soda and gas is released and you see all the bubbles, that is actually a physical change. And the release of the carbon dioxide bubbles is caused by the change in pressure. And so it's not a chemical change, but gas is often an indicator. Now, most chemical changes are not reversible, or at least not easily reversible. You can't unburn a cake, okay? You can't uncook an egg. It will never go back to being liquid. So, you know, your cooked cake can never go back to being cake batter. So a lot of chemical changes are irreversible, but there are some that are reversible, and the book does mention one, and I really can't think of many more. And that's like the body uses glucose to make fat, but then when the body uses the fat, it turns it back into glucose to use for energy. So that is an example of a chemical change that can be reversed and go back to its original state. Okay, chemical equations. So chemical equation describes how chemicals interact to have a chemical reaction that forms new chemicals. And so you put together the chemical formulas and the arrow that says that they are reacting to form whatever's on the other side and more chemical formulas. Okay, so the reactants of the chemical equation are always going to be on the left side, and then you have the arrow, and that means that they are reacting to form whatever the products are on the right side. Okay, so how I would say this chemical equation verbally would be sodium hydroxide, which is the NaOH, and hydrochloric acid, HCl, react to form. That's what I put in that arrow spot. Some people use some slightly different language, and that's okay. Sodium chloride and water. Now, when we are doing this, let's do this. Okay, so key point here that you need to understand about chemical equations. I'm not going to have you be required to balance chemical equations, but what you do need to know is this, that in the law of conservation of matter, matter can be changed but not created or destroyed. That means whatever atoms that you have on the left side of the chemical equation, you also need to have on the right side. So if you look at this one here, there is one sodium on the left side and one sodium on the right side. There is one oxygen on the left side and one oxygen on the right side. Hydrogen, I have two hydrogens on the left side and two hydrogens on the right side, one chlorine and one chlorine. Okay, and so that means that is balanced. I have the same number on both sides. Okay, so what balancing chemical equations is adjusting how many of each molecule is in the equation to make sure that you have the same number of atoms on both sides. Okay, so the last thing I want to show you here is making sure that you understand the numbers in a chemical equation. So the first one up top was kind of easy because there's no numbers other than the subscripts that we've already talked about that refer to the number of atoms within a molecule. But this one here is a little bit more complicated because we have numbers here. So if you aren't familiar with that, these are called coefficients, kind of just like in algebra. And they really mean the same thing. That number, and then there is 12 in this case of everything after that number. Okay, so if there is no coefficient, just like in algebra, it's an assumed 1. Okay, so that here there would be a 1 for this, for the C12H22O11. Okay, here there's 12 oxygen molecules. Here there are 12 carbon dioxide molecules. Here there are 11 water molecules. And so that's what that means. Now, when you are balancing equations, if you do choose to work on that in this class, because it's going to be optional for extra credit, the key thing is that you cannot change anything in the molecule, okay? H2O is a very different thing than H2O2, okay? H2O2 is hydrogen peroxide, and that has very different properties than water. You don't want to be drinking a lot of hydrogen peroxide. It would be bad for you. And so you can't just change numbers that are subscripts to make an equation balanced. The only thing that you can touch are the coefficients to balance an equation. Okay, here there's not a coefficient, but you could add one. Okay, so keep that in mind. Now, if you want to learn how to balance equations, if you don't know how yet and you want to do the extra credit, which the extra credit are some more on the simple side of balancing equation problems, because I think on all of them, half of it is balanced for you. But what I would recommend for learning how to do that outside of the book would be on the YouTube playlist for this chapter. The last 2 videos are, a lot of them are Tyler DeWitt, but the last 2 videos are Tyler DeWitt, and it's specifically about balancing equations. And that's what I would recommend watching if you want to learn or refresh yourself on balancing equations, okay? But balancing equations will only be extra credit homework and possibly extra credit on the exam. But I'm not requiring you do that. Other thing that I'm not requiring you learn about is Lewis structures, which I'll hopefully mention in class before you even watch this. Last thing, I'm going to give you another bonus point on the exam if you have watched this video all the way through and are hearing these instructions. Okay, so post a question on this YouTube video in the comment section by September 17th. And so some question on something in this chapter that you just need some further clarification on. It has to be about material in this chapter that I've covered in this lecture, or maybe I didn't cover it in the lecture, but it was in the chapter. It cannot be, is this going to be on the exam type of question, like ask about the material. So 1 bonus point if you can ask a question and post it as a comment on this YouTube video. You have to do this by September 17th. So you have all of this week that this chapter is assigned, all the way up until co-op day on the 17th, okay? By midnight that night. All right, y'all have a awesome week.